morning. This is the basic course on industrial instrumentation. As you know, the instrumentation is very important subject for in all process industry. As you know, in the industry, in the like steel, petrochemicals, then fertilizers, all this type of industry, the instrumentation is a subject which is concerned for everybody. The reason is there are various sensors in the instrumentation excuse me, and you will find that some of the sensors are huge in number, especially flow, temperature and all those things, and you have to measure, then you have to convert it in the some convenient domain which can be signal process later on and transmit those signal to the control room. Now, ultimately you know that all these measurements and instrumentation is basically to make your product or quality of the product better. Suppose in the fertilizer plants the quality of product should be good, urea, that means the purity of the urea, or in the case of steel industry, percentage of the carbon in the steel, all those things are important. And every step you will find we have to measure some parameters. What are those parameters? The parameters are pressure, temperature, flow, humidity, viscosity, pH, all those things. The reason that we have given the name of the course as a industrial instrumentation instead of instrumentation is that you see we will always focus on the to some process industries. That means what type of measurements they are doing and how that measurement is converted to electrical domain, so that I can get a current of 40 20 milliampere and all those things. Now, today is the first lecture, so obviously I will introduce the different components, and I will cover to some extent the static characteristics of the. I will cover full the static characteristics, and the dynamic characteristics I will start in the next lesson. In the lesson 1, let us look at the contents. The lesson 1, it is basically, as I told, introduction. The contents of this lesson is getting started, that means basic introduction to the system. Then I will cover the static characteristics. Now, the static characteristics, it means that the accuracy, linearity, sensitivity, etc., are the parameters of an instrument or sensor, and these attributes are collectively known as the static characteristics of an instrument and are given in the data sheet for a particular instrument. Now, at the end of this lesson, the viewer will know the static characteristics of the industrial instrumentation, the importance of instrumentation in process industry. Now, classification of instruments. So, instrument can be classified in 4 different categories. It can have active and passive instruments. Then, in the case of active instruments, you know that you have displacement sensors or potentiometer. So, in the case of displacement sensor or you can have, in the case of active instrument, that the displacement sensor, suppose I have a displacement sensor, it looks like this, that I have displacement, suppose I have a potentiometer like this, and I am giving energize it by battery, and I am taking the output voltage from this one. So, this is the wiper and or the jockey of the your potentiometer, displacement sensors, and I am taking the output from these two region. I am sorry, it should look like this. It should be I have a displacement sensor. So, I am giving this is our jockey, and I am taking measuring. So, this suppose this is the voltage E naught, if it supply the EX excitation voltage, and this voltage E naught. Obviously, you can see that E naught, if you displace it in this direction, suppose x. So, that E naught will be a function of x. If the x changes, our E naught also will change. So, in this case, we can find that this is a displacement sensor, and I need an excitation voltage here. If you do not give the excitation voltage, my potentiometer obviously will not work, and I will not get any output voltage there. So, this type of instrument I should call it, or we should call it an active instrument or active sensor. Now, there are some sensors which are passive in the sense, suppose I have a Bourdeau gauge which is used, and we will discuss that in later on. That Bourdeau gauge, you know, there is a C type of tube, it looks like this. I have a C tube, and this area of cross section of the tube is elliptical. Now, if you increase the pressure here, so the tube will try to make in circular form, that means it will have a circular form like this one. So, accordingly this tip of the our tube will move in these directions. So, this movement of the tip can be utilized to move some pointer on the scale, so that with some arrangements of rack and pinion and all those things, you can find that it will move on a scale like this one. So, in this case, that it will work as an it is a passive instrument, it is not an active instrument. Moreover, please note that active instrument does not mean it is only electrical. Active instruments can be also be pneumatic, because I have told about the active instruments which is only passive, but active instrument is also the, it can be pneumatic instruments, it can have also hydraulic instrument, where there is supply, always supply. Now, force balance systems, or you can flapper nozzle systems, most of you are familiar with, or we will cover this. I am sorry, you are not familiar with it right now, you will be familiar with the systems after some time, or after few lectures, that you will find that the flapper nozzle systems, you need always a power supply, I mean use a pneumatic supply. So, without supply the flapper nozzle systems cannot work. Similarly, hydraulic systems also, I need some hydraulic, some liquid, like oil or water or kerosene, that type of thing, so that it will be activated. So, that type of instruments are active instrument. And the choice between the active and passive instruments involves carefully balancing the measurement, the resolution, these are the requirements and against cost. The reason you see that in the case of just let us go back to again and to this potentiometer, you see that when we discuss the potentiometer, we have seen that we have the potentiometer here, we have a power supply here, and we are taking, this is our wiper which moves in this direction x, and I am getting an output voltage E naught. Now, you see that resolution of this potentiometer, that means output voltage, can be made better and better if I suppose if I increase the supply voltage value. Whereas, and this is very simple, I mean it is just increase the supply voltage E x excitation voltage, and the measurement resolution will increase, right. Whereas, in the case of the passive instrument, it is not very easy. Suppose as I told you, as I show you the Bourdeau tube which is used for measurement of measurement of pressure, or suppose one of the good example is a mercury in glass manometers, all of you are familiar with. How does it look? It looks like all of you have seen that we have a tube like this one, and then there is mercury bulb here. So, and mercury will heat up, it will go up like this one. So, in this case the resolution, if I want to change the resolution, it is not very easy task. So, you have to change the entire constructions of the system, that means the capillary should be more thinner and all those things, so that I will get for a smaller and smaller measurements of temperature. But that is not necessary in the case of electrical instruments, or suppose where I have some excitations, or pneumatic instruments or a hydraulic instrument, that we already discussed. Now, there are null and deflection type of instrument. This is very important, null and deflection type of instruments. You see that if I say here, how does it, what is this null deflection type? All of you are familiar with the Wheatstone bridge. How does it look? It looks like this. This is our Wheatstone bridge. I have a power supply here and I am measuring the output voltage here, E naught. Suppose this is R1, R2, R3, R4. Simple. I can write that R1 is equal to R4 by R3 into R2. Is not it? At balance, I can write like this one, when there is no, no current flowing through the detector. Suppose this is a detector or voltmeter. Now, null type means you see that I can utilize, suppose this R1 varies. Suppose R1 is a thermistor which is measuring some voltage, some temperatures, and this obviously what will happen, that if the temperature rises, the value of the R1 will fall. Now, I can utilize either R4 or R2 to balance the bridge. So, if I use some resistance R4 and R2, suppose R2 is also varying. So, in that case it is a null type of instrument. Whereas, if I utilize this, suppose whenever there is a this R1 initially, suppose all the equal. So, a bridge is balanced. Now, R1, since it is a thermistor, as the temperature rises, this resistance will fall. I will get an unbalanced voltage at the detector side. So, this voltage actually you will you can say that it is a, now the instrument down, now our system is a deflection type systems. It is no more a null, and means I can calibrate this output voltage. That means, I calibrate this unbalanced voltage in terms of the temperature or in terms of the resistance R1. So, that is possible. So, this is the difference between null and deflection type of instrument. Sometimes we prefer to have a null type of instrument, sometimes we prefer to have a deflection type of instrument, especially in the case of electrical circuits, when we need always some output voltage, we should go for the deflection type of instrument. But in some precisions we need a null, because always whenever the if you make the bridge null, obviously it is the most accurate form of measurement. Now, monitoring and transmitting instrument, what does it mean? It means that mercury in glass manometer, there is a good example of the monitoring instrument. Mercury in glass manometer, as you know, you have seen, or suppose a flow meter, suppose a rotometer, it is a common example of the, how does it look? Is rotometer, we will discuss in details in later on. So, it has an shape like this one, a vessel, and it is there is a float or bob. So, it will go like this one. So, liquid is flowing through this and going out. So, this liquid will move up and down, right? The liquid will move up and down, and these positions of the bob, can be calibrated in terms of the flow, right. So, this type of instrument is only monitoring instrument, you cannot say it is a transmitting instrument, right. Or mercury in glass manometer, that is also a transmitting instrument, because you are reading only the temperature. But suppose if I use a thermocouple there, instead of a mercury in glass manometer, if I use a thermocouple. In the case of thermocouple, what will happen? You know that you will get a voltage there. Whenever there is a difference of temperature between the two junctions of the thermocouple of the dissimilar metals, you will get a voltage there. So, that voltage can be calibrated in terms of temperature. Similarly, in the case of RTD or resistance temperature detectors, which is very accurate form of measurements of temperature, you will find also there that if the temperature varies, the resistance will vary. So, that change of resistance can be taken as I have shown in the last slide, that can be utilized as an unbalanced voltage. So, that unbalanced voltage can be calibrated in terms of the temperature. So, this is also because that signal can be transmitted. Now, one thing you should know, that in the industry, that usually or you cannot transmit voltage, you have to transmit current, even though it is not very relevant whether it is monitoring or transmitting instruments, but I am discussing this is important, since it is industrial instrumentation, you must know what is the practical aspects of the sensor signal conditioning circuitry. Any signal which is electrical in nature, you are not supposed to transmit voltage. Voltage, if you transmit, it will be totally corrupted by the noise. You have to transmit current. So, typical standard for industry is the 4 to 20 milliampere of current, that is for the total range of temperature, pressure, flow, etc. So, this is the difference between monitoring and transmitting sort of instruments. So, all the instruments, there are some instruments which are both monitoring and transmitting. That means, it has monitoring systems also, it is monitoring the temperatures on board. You will find the, on the panel itself you will find the temperature itself, also it has a transmitting capability. If it is has no transmitting capability, there is a transmitter which is to be utilized to convert that signal to the current domain. Transmitter is a very common form in industry, you will find that many times we are talking about this transmitter. The function of this transmitter is to convert the signal, whether it is pneumatic signal, electrical signal, hydraulic signal, to convert to 4 to 20 milliampere of electrical current. This will be transmitted to the control room for taking the control actions, which will be ultimately activate some of the control valve like this one, with to control flow or heating to the some heater or heating power to the heater and all those things. Or we can have analog or digital instrument. Now, in the case of analog instrument, output varies continuously. It's a, there can be infinitesimal positions of the pointer. Suppose I have a simple, if I say that if I have a simple voltmeter, suppose I have a voltmeter, if I take a, I have voltmeters, so what will happen? The pointer will move, is not it? So, I have a calibrated scale here in volts, so pointer will move. So, in a case of analog instrument, when you talk the analog instrument, you will find there is infinite position of the pointer. You can have many positions, whereas in the case of digital instrument, this is not the case. In the digital instrument, output varies in the discrete forms, it is not continuous. So, in that case, we will consider the digital instrument. Sometimes people talk about suppose a revolution counter, whether that is a digital, I will not consider that as a digital. Digital instrument so far is, today is concerned with talk of the digital instruments, where you have some digital circuitry and the output is also digital. Suppose if you have a virtual instrumentation, which is actually digital instrumentation, but we are showing that like a conventional analog meter. It is not necessary it is an analog instrument. So, in that sense, I say if the signal conditioning there itself inside the system is of the instrumentation system is digital in nature, we call it digital instrument, whereas in the case of analog instruments it has a analog in nature. But please note that in analog instrument there can be analog meter, there can be many positions of the pointer on the scale, whereas in the case of digital instrument there are finite number of positions of the output. This is all about the digital and analog instrument. Now, let us look at a process diagram which will show you, give you some idea of the instrumentation system and why we have given the name of the industrial instrumentation instead of simple instrumentation or instrumentation devices and all those things. Now, this is a typical process you look at, this is a typical process. Here you see that a liquid is flowing through this pipe and it is going out, right, and there is orifice plate. Now, what will happen, you see there is two tappings here, one is upstream tapping and another is downstream tapping. So, this tapping means that it will the pressure, the flow, whatever the liquid is flowing through the pipe. Our ultimate goal, I have a set point, some fixed value of suppose L liter per minute. That liquid I should always, or that liquid should always, this rate of the liquid should be maintained through this pipe. That is our ultimate goal. In many situations you will find this type of, whether steel, chemical plants, you will find this type of situations. It might be water, might be naphtha, and so many things are there where you have to measure the flow. Now, you see what will happen, that liquid is flowing. So, there is a upstream tapping and downstream tapping. What is the function? You will see later on, you see that in the case of flow meter, the flow is converted in terms of pressure, because as you know that when the liquid is flowing through this pipe, here the flow is whenever it is flowing through this region, the flow is high. If the flow is high, then what will happen, the pressure will drop. So, there is a high pressure zone and it is a low pressure zone. So, this I will take through a tapping. This is called upstream tapping and downstream tapping, and I am given to a DP transmitter. DP transmitter means is a differential pressure transmitter. Sometimes back people used to call it a DPDT, differential pressure differential transmitter, but nowadays more reasonably people call it just DP transmitter or differential pressure transmitter. Why it is differential pressure? Because you see, I have to measure, I have to look at, I have to take the tapping both upstream and downstream. So, because these are restrictions, so this we call upstream, this is downstream, and this differential pressure is going to a DP transmitter. Now, this DP transmitter is, I mean, according to flow, it is giving a signal, pneumatic signal of 3 to 15 psi. PSI means pounds per square inch. Even though this nowadays, as you know, it is an SI system, but still in some cases people use more convenient with the PSI, which for some reason, even though while we solve the problem, we will find that we are using SI system, but still industry will they use this type of units. It is not a problem. Now, this 3 to 15 psi of pressure, that means varies. That means for almost no flow, I will get a 3 psi of pressure. For full flow of the liquid, I will get a 15 psi of pressure. So, this flow, I mean, this will go to the a pressure to current converter. Now, pressure to current converter, what it will do? It will convert that signal, pneumatic signal, to the current domain. As I told you earlier, you see that you have to transmit the pneumatic signal, electrical signal, hydraulic signal to the electrical domain. So, 4 to 20 milliampere of current. Now, what is this 4 to 20 milliampere? As you say, it is from for 3 psi, I have a 4 milliampere of current. For 15 psi, I have a 20 milliampere of current. This range you have to maintain. Whatever the range of the flow, it does not matter, because accordingly it will be, because this will remain constant. It might be in a huge flow, might be, it can be 10 to the power 5 liter per hour, that type. Suppose in a power station, water pumping station, all those things, a huge amount of liquid is flowing, or in some narrow pipe that might be, it is few, I mean a liter, it does not matter. The range will be always, which is converted, will be always 3 to 15 psi for the pneumatic signal, and for the current signal it is 4 to 20 milliampere. But nowadays, as you know, this thing, entire thing are incorporated in one DP transmitter, where you will get directly this 4 to 20 milliampere of current. This load, you do not need P to I converter and all those things, everything is incorporated inside. So, we will see that you will utilize this differential pressure to make will utilize it for a change of positions of a diaphragm plate in the case of capacity measurement. So, that I will get differential of capacitance, we will discuss later on, and accordingly I will get a current. Now, this current is coming to a controller. The controller, the function of the controller is to give a control signal to the pneumatic control valve. I have a set point, because what is set point? Set point will set the value of the flow of the liquid, L liter suppose, or suppose 1000 liter per minute, or that type of very high 1000 liter per minute, or I should say 1000 liter per hour, that type of set points we have done. Now, if for some reason or the other, if this falls, then what will happen? I have to open the valve, so the more liquid will flow, or for some reason or the other, suppose that this has increased, that means flow has increased, then what we will get? I will get a flow, I have to close the valve, right. So, that type of signal you have to you have to put to the control valve. So, that control, where I will get that signal, I will get the signal, I will subtract this signal. I have a set point, I have a signal. So, these two signal will be subtracted. When we will future we will study the control systems, we will find all those things in details. That means, I have a systems here, and I have this is our set point, and this is our error. So, this will be kept and this will come to the controller. Okay. This I have a process, it will take actions, or it like this one anyway. So, I have a, that means, I have a controller process, I have a measurement, it is coming like. So, this is our set point. This is our output from the DP transmitter, right. So, this is coming our. So, our goal is to make this R equal to C. That means these two should remain same. If there is a difference, I will get a error voltage. So, our controller will take some actions. So, it will send some signal to the control valve and all those things, it will take some action, it will make, so that it will move in such a direction, so that T s will be again 0, right. Here also it is same, you see that what will happen, that if it increases, if the flow increases, my valve is to be closed. So, this flow, if the flow increases, this current will also increase. So, there is a set point, there is a error. So, this is the error signal which is coming from this error signal also should be 4 to 20 milliampere, because I cannot transmit anything other than 4 to 20 milliampere. So, this will come to the, because this valve is pneumatic. Most of the industrial valve, as you know, is a pneumatic valve, because in many industries like the especially hydrocarbon industries and all these things, petrochemical industry, all these things, you cannot use our solenoid valve, electrically operated valve, because of the safety reasons, because the operating voltage should be below 50 volt. So, there is a restriction. So, if for a large pipe and all those things, I cannot use there all those small control valves. So, I have to use pneumatic control, but pneumatic control valve means that signal should be pneumatic. To close or open, so to close and open, I have to give pneumatic signal. So, ultimately what is that? That very precisely, or I should say that if the flow is increased, so I will get a signal through this transmitter, this will convert to the current domain going to the controller. I have a set point. So, obviously, if flow has increased, there is a error voltage, it will come. So, the stem of the valve will go down, the flow of the valve will be controlled. This action will take until and unless this error signal will become 0, right, or this current and this set point will remain same. It is in other way also, if the flow suppose decreases, then what will happen, that if the flow decreases, I will again also get some error voltage, but of opposite sign obviously. So, what will happen? So, I have to take some action, so that the control valve stem should go out, so that I will get a flow which is actual to the set point. So, the action will be taken until unless this error current will become 0, right. Now, with this I will go to the instrumentation laboratory of IIT Kharagpur. So, where you can see some of the instruments or process instruments, you will get the glimpses of how it looks like and how the different flow meter works and what actually the process looks like. We have some small process by which you can get the idea of the what is the instrumentation system we talk about. We will come back after some time. This is the a flow and level control system, which is actually the scaled down version of the actual process, and what actually it is the system is doing, that it has different sensors. What I want to mean that you see the instrumentation is everywhere. You will find that there are several sensors, there are float level sensors, there are flow sensors, there are several control valves. So, the goal of this process is that basically to control the level as well as flow in a particular process. Now, the several sensors will will play actually very key role in the system, because you see everywhere you will find that the sensors output is most important for actual control of the whatever the control systems you are using, that's it's important, as well as whatever the sensor output which is coming from the sensors is also important. So, the sensors calibrations, its accuracy, its resolutions also will control the basic process. Any process has some output. It has some, suppose if you go to the petrochemical process, it has some diesel output or petrol outputs or kerosene outputs or any other type of materials. Or if you go to fertilizer plant, you will find there are different types of fertilizers are coming out. But the quality of the fertilizers or quality of the diesel, quality of the petrol will ultimately decided by not only by the control algorithms which you are using in the plant, as well as by the sensor. If the sensors are not accurate, if the instrumentation system is not accurate, then you will find that the entire quality control is out of order. So that this tells that how instrumentation is important in industry. Now I will describe at least two sensors. One of these is, you see, there is a rotameter, which is a flow meter. It will give the estimate of the flow of the liquid in the entire process. Now you see in the rotameter there is a taper tube with a very small angle, and the liquid is coming in through this side and the liquid is coming out through that. And there is a float, in some the technical persons they call it bob also. As the liquid flow increases, this bob will move up. Now the details of these different forces which is acting on the floor will be discussed later on. Now you can just remember here what will happen, that when the float goes up, that means the liquid flow also increases here. Here you can see here there is one float sensor, which is a potentiometric float sensor. Due to the different level of the, you can see that this liquid can go up. You can see here this float will go up like this one as the liquid goes up, and potentiometer will move and it will give the electrical output. Now any process or any instrumentation system, one thing you must remember, that which will be discussed later on also, that you cannot transmit voltage, you have to transmit current. Now for that reason you see here we have a float level transmitter which will transmit 4 to 20 milliampere current to the process. This system, first it will go through this cord, it will go to the process interface. From the process interface, it will come to the digital computer. Now from the digital computer there are control algorithm by which we can set the different algorithms. You can tune the controller, it will feedback the system to the process controller. Process controller will take the action, then the signal will go back through this cord again to this control valve. Control valve will make the decision of the flow. Accordingly, you can achieve the particular flow or particular level in this process. This is the miniature versions of the actual process. Actual process might be large, but whatever the components you can see here, this you will find also in the process. In this assembly, you can find several flow meters. There are rotameters, there are optical flow meter, there are hot wire anemometer, and there is also a magnetic flow meter. On the top of it you will find there is a weir which is called V-notch weir. As you know, the flow meters are different types. These are, some of them are for the open channel and some of are for the closed channel. This V-notch weir is basically an open channel meter, which will give you the extensively used for the irrigation purposes, so that how much water is needed in the or different fields to get the estimate of that. Now you can see that if you increase the flow here, by this you can have a pump by which you can increase the flow. You see the flow is, I have reduced the flow, so the bob of the flow meter is coming down, and this tapered glass is calibrated in terms of centimeter cube per minute, so it will give you the flow, and this height is also calibrated in terms of flow. And you can see here, interestingly, this is one electro-optic flow meter. If I go to the back side, you can see that there are 4 spots and there are lights which is falling on the flow meter, and for each complete rotations I am getting 4 pulses. So accordingly, suppose if I have 10 rotations, so accordingly I can calculate how much the flow is moving. So it has a direct electrical output. Otherwise, you can see here this flow meter has no electrical output. Similarly, hot wire anemometer also has electrical output, and this is the hot wire anemometer. We cannot see from here because it is inside. And in the magnetic flow meters also it is electrical output. So all these flow meters except this rotameter has electrical output. Now electrical output has advantages. If you have an instrumentation system, so electrical output, you can directly convert that signal to the current domain. 4 to 20 milliampere of current domain, then you can digitize it if it is necessary. Whereas if you have some non-electrical output, either pneumatic outputs or some mechanical movement, that type of things, you have to convert these to the electrical domain by using either new electric converters sort of thing, or any other form of devices. So this will give you the glimpses of the different flow sensors which is used in the industry, in the process industry. Flow meters you will find in any process industry. These are thousands in numbers. Unfortunately here I cannot show you and all that type of thing, but this will give you the idea of how the flow measured in the process. See here at the back side of this flow meter system, even though you cannot see here clearly the hot wire anemometer, which is also a resistance based flow meter, and electromagnetic flow meter, but you can see here the electro-optic flow meter. You see what will happen in this instrumentation system, that there is a light source which will be launched, and there are 4 spots on the back side, or 4 white spots on the back side, 4 white or silver. So light will get reflected from that, and there is a receiver on the other side. So what will happen, that when it rotates, for each complete rotation of the system, you will get 4 clock pulses. So if I can count the number of clock pulses, which obviously you have to, you have to little signal process, you have to make little signal processing, in the sense that you have to pass the signal shaper like Schmidt trigger. You will get output and that can be counted for 60 minutes, so that you can get the flow, because if you know the flow pipe diameters and all those things, you can immediately tell that how much is the flow rate in a minute. So this will give you the direct electrical output, obviously, that can be processed, that can be easily interfaced with the computer. So this will give the glimpses of the different flow sensors in the system. And this can be calibrated obviously with the rotometer, which is in the front sides, which I have shown at the beginning of this lecture. Welcome back to the classroom. So we will now study the instrument characteristics. The static characteristics of an instruments are concerned only with the steady state readings. Okay, it is not concerned with any transient readings. So we will only concerned with the steady state reading. So we will call one by one. Now we will read one by one the different static characteristics. First of all, the span. Now if in a measuring instrument the highest point of calibration is x2 units and the lowest point of calibration is x1 units, I can tell the then the instrument range is x2 units and the instrument span is x2 minus x1 units. It is very simple. That means suppose if I have a total range, suppose I have an instrument temperature sense which can measure 5 degree centigrade to 200 degree centigrade. In that case, range I will call it 200 degree centigrade, span I will call it 195 degree centigrade. Now mean and standard deviation of measurements, we will need this in future, you will find, that is the reason we are explaining. Suppose we are making a set of n measurement x1, x2, xn, and the mean value will be given by x mean x1 plus x2 plus so on xn upon n. This is x mean, this is the mean of the measurements, and the spread of any measured value xi can be expressed as a deviation, which can be expressed as given as di equal to xi minus x mean. The extent to which the measured values are spread about the mean value are now be expressed as standard deviation sigma, where sigma equal to d1 square plus d2 square so on dn square upon n minus 1 whole to the power half under the square root. So this is the standard deviations. We need it in future, so you will find that is the reason we are explaining it here. Now accuracy actually means accuracy and precisions. Accuracy is usually expressed as accurate to within x%, even though we have not exactly used the same word. So accuracy and accurate slightly different. It is usually we don't like that if somebody express the same word, some definition with the implanted in the same word in the definition itself, but these two are different. So accuracy, we will explain this more. Accuracy is usually expressed as accurate to within x%. It means accurate to within plus minus x% of the instrument span at all calibration points of the scale unless otherwise stated. When a temperature transducer with an error of plus minus 1% indicates a 100 degree centigrade, the true temperature is somewhere between a 99 degree centigrade and 101 degree centigrade. Thus, the measurement accuracy of plus minus 1% defines how close the measurement is to the actual measured quantity. So, this is the main text. Thus, the measurement accuracy of plus minus 1% defines how close the measurement is to the actual measured quantities. How much is the deviation, that is actually the, we talk about the accuracy. Linearity, the calibration is very important, because in instrumentation, you know, always we prefer a linear sensor. There is a lot of problem if you don't have a linear sensor. You will find that what it means the input output relation should be linear. Forget about the accuracy. We can have I can have a characteristics like this one also. I can say it's a non-linear, but it can be very accurate. But if it is linear, ease of calibration will be there. That means that if I can calibrate an instrument, if it is linear instruments, its calibration is quite simple. Its sensitivity will be same at all positions. Why? You see here, I have this type of. So it does not matter where I take the sensitivity. Sensitivity will remain same. Whereas if you take some other, suppose here in this curve, sensitivity will something here and it will somewhere here, it will be different. So while you are making the signal conditioning circuitry, it will be very difficult. The task will be very hard. That means your amplifier should also be adaptive. It is very difficult task. So always we prefer linear instrument, but some instruments, some sensor like thermocouple, thermistor, it is non-linear sensor. We cannot do anything because of its low cost, easy repeatability. There are so many other positive points. We have sacrificed that it is a non-linear. I mean, we want to accommodate it, even though it is a non-linear sensor. Now, it is normally desirable that the output reading of an instrument is linearly proportional to the quantity being measured. Figure 1.2 shows a calibration curve, that is a plot of the typical output reading cross marked of an instrument when the sequence of input quantities is applied to it. We will show in the next slide. A good fit straight line will give the calibration curve of the instrument. How does it look? Nonlinearity is thus defined as the maximum deviations of any of the output readings marked with a cross from the straight line, and it is usually expressed as a percentage of the full scale reading. You see that we talked about the figure 1.2 measured quantity. You see here that this is our measured quantity. So, we make a best fit curve. There are various softwares available. So, by which least square method is that, by which you can make a best fit curve, so that it will be a best fit for all the points which you are given. So, this is our deviations, okay, is not it? I mean, that means this is our deviations, this is our deviations, okay, this is our deviation, this is our deviation. So, this nonlinearity is thus defined as the maximum deviations of any of the output readings marked with a cross from this straight line, and it is usually expressed as a percentage of full scale reading. Always it should be expressed in percentage of full scale reading. Now, tolerance, it is a term that is closely related to the accuracy and defines the maximum error which is to be expected on some value. It is not exactly a static characteristics, obviously you know that, however, some instrument manufacturers usually quote that, quote this tolerance figure. So, you must know what is the tolerance. One of the good example, those who are not familiar with the instrument tolerance, it is that maximum deviation of a manufactured component from some specified value. You are familiar with that. Why? You see, for an example, a resistor having a nominal value of 100 ohm and a tolerance of 5% might be have an actual value anywhere between 95 ohm and 105 ohm. There are resistors are available of various tolerance, 1%, 10%, 2% depending on. So, if it tolerance band is important, because not always you will find the 0.1% tolerance. If you with a 5% tolerance, measurement is okay, there is no problem. Why it is saying, I am saying, you see that if my measurement error is a 5%, that means tolerance band is coming 5%. Ultimately, what will do with this such a precise measurements? Ultimately, the quality of the product. If the quality of the product does not deteriorate, I can allow certain amount of tolerances. Is not it? If it is not, if the product ultimately product falls Suppose in some chemical plants, and you can I have to precise if there is 5 degree centigrade temperature variation. Suppose there is a you are controlling some temperatures of suppose 600 degree centigrade. It hardly matters if the temperature varies to 598 to 602 degree centigrade. Whereas in some process, suppose in the case of bioprocess, you will find that where the cell grows in that type of situation, if the difference of temperature of 0.5 degree might be detrimental to the cell will die. So, in that type of situations you cannot allow the temperature to. So, these are tolerances are there so everywhere. Now, static error, it is the difference between the true value of a time invariant measurable quantity and the value indicated by the instrument. The static error is expressed as plus y units or minus y units, and for static error in units, true value plus static error is the instrument reading, or true value equal to instrument reading plus static correction, quite obviously because it is opposite of that is a static error. Now, repeatability is very important, is repeatability is in instrumentation. If you see that the if you there are thousands of instruments in a big plant, thousands of sensors, so temperature, pressure, flow, you cannot expect that you will calibrate the instruments every day or every once in a 7 days. Usually the typical norm is that there is routine maintenance, routine checking of all this calibration, but if there is a if the fall of quality of some of the, then we will talk, and for some of the product we will talk about the instrument calibrations or sensor calibrations, otherwise not. So, repeatability is defined as the of an instrument is the degree of closeness with which a measurable quantity may be repeatedly measured. What does it mean? Suppose I have a voltmeter. So, I am giving a battery voltage. So, battery voltage is suppose a dry cell, battery voltage is fixed 1.5 volts. So, if I even measure 1000 times, it should always give 1.5 volts by that instrument or voltmeter. I would say that this repeatability is good, because battery voltage is not changing, supposed to. Suppose it is dry cell battery, if you are not drawing any current from that much, because usually voltmeter does not draw much current. So, it is if you take the 1000 reading, it should give you this exactly same value 1.5 volt. If it does not, that means the repeatability is poor. Now, mathematically, how will you define this repeatability? Mathematically, it is defined as the measure of the variation in the measured data known as the standard deviation sigma. It is expressed in terms of maximum repeatability error as a percentage of full scale output range, right. So, it is repeatability 2 sigma full scale output range into 100, this is a percentage repeatability. Now, static sensitivity is very important. The slope of a static calibration curve evaluated at the input value yields the static sensitivity, right. It means that as shown in figure 1.3, will show it will come. The static sensitivity at any particular input value, say x1, is expressed as this. This is a figure 1, you can see here. So, this is a calibration curve, this is my input, sorry. Yes. You see here, there this is our calibration curve. This is our calibration curve, right? It is going like this. It is not linear. It does not matter. So, you see here that this is my input and this is output reading. The input is some parameters and output we are getting some reading. Excuse me. The static sensitivity is defined as at x1 value. Suppose if I say this is the x1, at the value x1, the slope of this calibration curve. So, it is dy by dx at x equal to x1. Interestingly, you see the static sensitivity varies. You see here is some, there is some value, here it is some different value. So, the static sensitivity for the nonlinear curve will change. It depends on the what point you are measuring, right. You will find this typically true that in the case of thermocouple. Thermocouple you will find that typically we say some range. Suppose of the platinum rhodium thermocouple, we say that the static its sensitivity is around 10 to 12 microvolt per degree centigrade. It is non-linear. Suppose in some range you will find 10 microvolt per degree centigrade, some other range you may find 12 microvolt per degree centigrade, some other range even less, might be 6 to 7 microvolt per degree centigrade. Now, calibration actually it is very important. It is a procedure that involve a comparison of the particular instrument with either a primary standard number 1, a secondary standard with higher accuracy than the instrument to which to be calibrated, or a known output source, right. What does it mean? It is a primary standard, that means I can calibrate my instruments with a very accurate instrument by going to some national laboratory or some other places. I can calibrate that instrument with a secondary standard of higher accuracy. I can use some other instruments which I know they are accurate. So, I can calibrate, because you see the it is hardly in industrial instrumentation that you find that the instruments are of absolute type. That means you don't, it does not need any calibrations. You have to calibrate each and every instrument. So, most of the instruments you will find in that cases what will happen, that I must calibrate either with some primary standard. Suppose I have a I have given you a RTD. So, you must calibrate that with some small range. Suppose I can calibrate with some standard mercury glass manometers. So, I can calibrate like that, or I can calibrate with some, suppose boiling water, which is supposed to be for normal pressure and temperature. Normal pressure it should be 100 degrees centigrade for the pure water. So, that way we can calibrate, right, or I can calibrate with a known output source. What is that? I will show you. For an example, a flow meter can be calibrated with a standard flow meter available in the national laboratory. This is number 1. Number 2, it can be calibrated with another flow meter of known accuracy. It can be directly calibrated with a primary measurement such as weighing a certain amount of water in a tank, or a recording time required for this quantity to flow through the meter. How does it look? It looks like this. It looks like, suppose I have a flow meter, I have a vessel. So, I know how much is the height, I know how much the water is flowing out to this one. So, I can tell what is the flow rate, because if I have a stopwatch I can tell. So, this is some other form of calibration. So, I know the quantity of water, I know that time. So, I know the volume. So, I can find the volume rate, that means V by time. If I, so I can liters per minute, I can tell that how much the volume. So, I can calibrate in that way also, right. Now, dead zone or dead space is another important factor. Now, in many instruments you will find it has a dead zone. Dead zone is the largest value of a measured variable for which the instrument does not respond, right. What does it mean? Suppose I have a pressure gauge which is measuring a pressure of 10 to the power 5 psi. So, in that type of pressure gauge, you will, if you give a 50 psi, you will find that there is no movement of the pointer. So, that is the 50 psi is the dead zone of that type of instrument, right. So, dead zone usually occurs with a friction in a mechanical measurement system. Hysteresis is another important. Hysteresis error refers to the difference between the upscale sequence of calibration and downscale sequence of calibration, and the hysteresis error of an instrument is given by y upscale minus y downscale at x equal to x1. What does it mean? It looks like this. The hysteresis error is depicted in figure and is usually expressed in terms of the maximum hysteresis error as a percentage of full scale output range. Hysteresis error equal to hysteresis maximum hysteresis error upon full scale output range multiplied by 100. It looks like this figure you can see here, you see. So, this is our hysteresis error at x equal to x1. So, this if you take the full scale output range, so I will get a total hysteresis. So, is a, or I should say that it is a non matching of the upscale calibration and downscale calibrations. It may happen in some instrument that it does not match. In that case, we will call it hysteresis. The input impedance at the input of each component in a measuring system, there exists a variable xi1, and at the same point there is associated with xi2 another variable such that the product has the dimension of power. When these two signals are identified, we can define the input impedance as shown by Zi equal to xi1 minus upon xi2. This is important because some instrument and the So, here the power drain is P d equal to xi by xi1 square by zi, and that large input impedance is needed to keep the power drain small, because in some instruments, some sensor you will find like a pH meter, all this, it needs very small, should draw very small current. So, this is very important, because if it draws large current, it cannot measure the voltage actually, because it has internal large source impedance, right. Now, resolution is another important. This measurements precision of an instrument defines the smallest change in measured quantity that can be observed, right. Suppose I have a thermometer 0.2 degree centigrade is the minimum, so it is again 0.2 degree centigrade. For example, it looks like this. It is in a temperature transducer. If the 0.2 degree centigrade is the smallest temperature change observed, then the measurement resolution is 0.2 degree centigrade. Now, bias is another important. It means a constant error exists over the full range of measurement of an instrument. The error can be easily removed by the calibration. For an example, a voltmeter perhaps shows a reading of 1 volt with no input voltage to its terminal. If now a known voltage of 30 volt is applied to the voltage, the reading should be 31 volts. So, obviously, this constant bias of 1 volt can be removed by calibrations or by simply mechanical electrical means, suppose by adjusting the needle, or in case of auto voltmeter. So, I mean, we should take care with charge some capacitors when there is no input voltage, so that bias voltage will be charged. Accordingly, it will be subtracted or added to the final value when you are measuring some voltage. Drift is that the calibration of an instrument is usually performed under some control conditions of temperature and pressure, because not always we have a control condition. So, there will be drift in the measurements. As variation occurs in the ambient temperature, etc., some static characteristics change, namely 0 drift and the sensitivity may change, 0 of the instruments may change. So, 0 drift, it describes the effect where the 0 reading of an instrument is modified for the change in ambient conditions. And for an example, the 0 drift of a voltmeter, for the ambient temperature change is expressed in volts per degree centigrade. This is sometimes called the 0 drift coefficient related to the temperature changes. If there are several environmental parameters, then it will have a several 0 drift coefficient. Effect of 0 drift is to impose bias on the instrument. Sensitivity drift is another, because sensitivity also may change. It defines the amount by which an instrument sensitivity, defines the amount by which an instrument sensitivity of the measurement varies as ambient condition changes, right. So, this is all about the basic introductions of the industrial instrumentations. I will give the static characteristics in details, and you understood by this time what is the role of the instrumentation and how important it is, and the responsibility of the instrumentation engineers to maintain all those sensors, signal conditioning circuitry type of things. This ends the lesson 1.